Good evening, ladies and gentlemen. In this lesson, we're going to be looking at the section on electromagnetism or electrodynamics. So just so you're aware, this section comprises two subsections. We're going to start by looking at motors, and then we're going to move on to looking at generators. Please, there is something that I need to put in as a disclaimer. I'm covering the NSC curriculum, which means that we are not going to be going into great detail in Faraday's law initially, but I'm quite happy if anybody does IEB and they want to stay afterwards and they want to ask me particular questions about magnetic flux linkage or anything else like that, you are welcome to stay afterwards and ask those questions. But we're actually really lucky with the NSC that they don't examine us to that level of depth, so it makes it really nice and easy. We don't have to go into it. But if there is anybody who is doing IEB and they are struggling with it, I promise I'll stay a little bit at the end and we can go over anything that you're stuck with. I can quite easily explain magnetic flux linkage to you. All right, so without further ado, let's get started. Okay, so the first thing that you need to know, just quickly. Okay, the first thing that you need to know is that in the section of electrodynamics, we have two parts. We're going to be looking at motors, which fall under the motor effect. And we're going to be looking at generators, which exist because of electromagnetic induction. Please note, electromagnetic induction is based on two laws. The first is Faraday's law. And the second, which I guess explains the directions a little bit more, is Lenz's law. The key ideas that I want you to have is when we're looking at the motor effect, we are effectively turning electrical energy into mechanical energy. Specifically, the mechanical energy that'll be kinetic energy, but we can get away with just saying mechanical energy. And with generators, what we're going to do is we're instead going to turn mechanical energy, anything that allows us to rotate something. So that could be, in a generator, you could actually use a nuclear power station to cause steam to be boiled, water to be boiled as steam to rise, to turn a giant turbine, which provides the mechanical energy, and that will be then converted into electrical energy. All right. So I am going to start right now by specifically looking at motors. Okay. So I'm going to quickly clear everything. This is just a general overview. To give you an idea, I always teach motors very thoroughly. I've already mentioned to everybody that motors is not a huge proportion of your exam. If you're lucky, it'll give you, I think I've seen one paper where it was 6 marks. But the point is, if you understand motors, then for me to teach you generators is quick. All right. So we're going to get started with motors. But before I teach you about motors, I want to explain to you one of the phenomena that we discover. We discovered that when a current flows in a conductor, any conductor. In fact, this rule even applies if a current flows and you don't have a conductor, which you can have if you have a beam of electrons or a beam of alpha particles or a beam of charged particles moving. So when a current flows in a conductor, it generates or creates a magnetic field around the conductor. The way that they first discovered this, rather simply, was that they had a piece of wire and then they put little compasses around it, okay, like little compasses that you use for direction. And what they discovered was that all of the current needles deflected. And they ended up forming this like nice little circular pattern that went around the current carrying conductor. And that's how they figured out what was happening. Please, when I say it went around it, it's a little bit like my hand creates a round pattern here around the conductor, which is represented by my stylus. So it's that kind of angle. So when I'm talking about this being created this way, it's a little bit tricky, but I probably should be describing my direction of current through the wire, or the fact which way the wire is going, as the wire would normally go at an angle. So this is technically kind of perpendicular. So if the wire is that way, it's perpendicular to it. All right, so that's how they figured it was working. So around a current carrying conductor, a magnetic field is created. Now, in order to explain this idea fully, we're going to have to introduce a couple of new symbols. Hopefully, I'm not introducing them for the first time, and I'm introducing these two symbols. Hopefully, you've all encountered them a number of times before. The circle with the dot represents out of the page, and a circle with the cross represents into the page. What this is actually showing you is if I have a dot or an arrow, okay, oh, that's a very bad dot or arrow. Okay, let's pretend I have a dot or an arrow, and at the back here, I have these crosshairs. I don't know if any of you guys, my arrow is not doing a good job. I'm going to try and draw a slightly better arrow. I normally just do an arrow like that. So if you imagine an arrow or a dot, like you'd shoot into a dartboard, if you're looking at it from the back, you would see these little crosses going away from you. So that is showing that the arrow or dot is moving away from you, and you're looking at the back end of it where you see the cross. If you are looking at it from this side, just for the record, that picture's an eye, what you will see is you will see the point coming towards you. So instead of describing these as into or out of the page, I could describe this as away from you and towards you. Now, you're going to find that they use these symbols a lot, because when we draw things on a flat piece of paper, it's very easy to draw up, down. I call that up. That's up on my piece of paper. To the right, to the left. But into the page and out of the page gets tricky, and we've now just solved that problem. So we've mentioned that there is a magnetic field around the current carrying conductor. What we're now going to do is I'm going to describe to you how to determine which direction the magnetic field goes. So what we're going to do is we're going to use our right hand, and you're going to give me a thumbs up. In fact, right now, I'm going to stop sharing, and I'm going to ask anyone who has their camera on, or anyone who's got a camera that works, to quickly turn their camera on and give me a thumbs up with your right hand. It's got to be your right hand. I find giving a thumbs up with my left hand feels really doof, but a thumbs up with my right hand is there. Is nobody going to give me a thumbs up? Oh, yay, some of you, thumbs up. Right hand, thumbs up, yay. Thank you. All right, so we specifically have to do this with our right hand. I find if I give a thumbs up with my left hand, it feels half-hearted. It's got to be your right hand. And in this case, what happens is that your thumb shows the direction of the current. So there's my thumb. I've got a special hand. I'll even give myself 4 fingers. Okay, my thumb shows the direction of the current. I is the symbol for current. And my fingers show the direction of the magnetic field. Those of you who did this section in grade 11, which should be most of you, will hopefully know that the magnetic field strength is given by the symbol B. So I'm going to describe it as magnetic field there. That means that whichever way around I'm going, if the wire is going this way, we imagine that we're gripping it. And if the magnetic field goes around this way, then the current must be going up. If the magnetic field goes the other way, then the current must be going down. So one of the easiest ways to then look at this is if I were to imagine a current carrying conductor coming out of the page towards me, I'll hold my thumb towards myself, right hand. And when I do, if I look at the direction of my fingers, according to what I can see, my fingers very clearly are going around in an anti-clockwise direction. So my magnetic field can be drawn by concentric circles going around in an anti-clockwise direction. Please note, there's technically a rule that I'm not really showing here, but the further away you get from the current carrying conductor, the weaker the magnetic field is, which means that these lines should later actually end up getting further apart because the magnetic field is weaker. All right, So our direction of our magnetic field around the current carrying conductor is shown by these magnetic field lines. Okay, I'm hoping that at this point this makes sense. So everything that you should understand up till now is that when a current flows through a conductor, it creates a magnetic field around the conductor. And the direction of the magnetic field can be determined by using the right-hand thumbs up rule. Some schools do different versions. I find this is by far the easiest. Right-hand thumbs up, your fingers curl around in the direction of the magnetic field when your thumb points in the direction of conventional current. One more important thing, which way round does conventional current go? Well, on any circuit, even a circuit with nothing else in it like I've drawn there, the long end of the cell is positive, the short end is negative, and your conventional current goes from positive to negative. I mention this because sometimes they're not going to put in which way the conventional current goes in a diagram. They're going to give you a cell or a battery and expect you to be able to determine which way around the current carrying conductor, well, which way around, sorry, the current goes. All right, ladies and gentlemen, I hope you understand everything so far, because we're going to use this idea just now to show the motor effect. All right, so I'm going to quickly clear all my drawings, quickly take a screenshot if you need any of all of my scribbles, and we're now going to talk about the motor effect. So the motor effect uses the fact that this little current carrying conductor creates a magnetic field. And the motor effect basically says that when a current, that's a U, let's just undo that. When a current carrying conductor is placed in an external magnetic field, it experiences a force. If it experiences a force, force can cause motion. So that is where the motor effect bit comes in. The motor effect idea comes in that a force can cause motion. Okay, motor effect literally comes from the word motion. So I'm now going to explain to you how this happens. Please note the diagram that I'm drawing for you here is an explanation diagram. A lot of what we're doing tonight is explanations so that you have a clear picture in your head as to why the easy answers that you're going to give later apply. The questions are much easier than what I'm doing here, but I'm actually teaching you how it works. All right, there is a much easier way to determine which way the force works, which you're just going to learn later, which uses your fingers like this. Some schools do a funny thing with slapping. I don't even know which hand you use to snap the table. I'm going to teach you Fleming's left-hand motor rule just now. But first of all, I want to explain to you why Fleming's left-hand motor rule applies. So if I have an external magnetic field drawn here from north to south, and just a quick thing, I'm going to remind you, magnetic fields always go from north towards south. And if you have two parallel magnets, as I do drawn here, the magnetic field is going to be uniform. So these lines that I'm drawing are beautifully straight lines that are very parallel to each other and equally spaced. Now imagine I put a current carrying conductor between these two. You can see from the fact that there is a cross there that this current carrying conductor is moving away from you, as in into the page. If you're looking at a screen right now and your screen is horizontal, it's going bye-bye away from you. Okay, so if I look at this direction and I want to work out which way around the magnetic field is around the current carrying conductor that I've drawn there, I'd have to take my right-hand thumb, point it away from me, and if I look at my fingers, from my side, my perspective, my fingers curl around in a clockwise direction. If you look here, you should hopefully see that my fingers curl around in a clockwise direction going away from me. I hope it worked that way. So if I do this, it's going away from me, clockwise direction means that we're going to have a magnetic field going around like this, but it'll be clockwise. The key idea that I want you to get is at the top, it'll go that way, and at the bottom, it'll go that way. Now, the reason that I care about which way it goes is that this little current carrying conductor's magnetic field is going to interfere with the big magnetic field. If you look at the top, both of them have magnetic fields that go in the same direction. At the bottom, they have magnetic fields that go in opposite directions. So what we end up with at the top, and please don't ever write this in an exam because it's not exactly correct. At the top here, we're going to have like a buildup of magnetic field. I like to imagine it like this huge pressure, even though it's not a pressure. And at the bottom here, they're going to cancel each other out. And we're going to have almost like a vacuum created. So here, we end up with no magnetic field or a very weak magnetic field. What then happens is, in order to remove this buildup, where you've got a huge amount of kind of magnetic field pushing away and nothing down here, this current carrying conductor, I don't know if everybody can see that line very clearly, is going to experience a downward force. And it's literally, if it's able to move, going to move towards the bottom of my page here, because it is experiencing a force. Now, I always draw a bit of a weird analogy at this point, where I go and say, my strange analogy for this is, imagine that I decide I want to go and set up my own little shop, okay? And I want to, with setting up my own little shop, I want to go and sell lemonade. And I decide, cool, I'm going to sell lemonade. So here's my little magnetic field, which is my selling lemonade. So then I have a brainwave. Where is the best place to go to sell lemonade? I need a market. Okay, I need people to be there. So I think a little bit harder, and I go, you know what? I'm going to go into the middle of a Woolworths. I'm going to take my little table. I'm going to take a tablecloth. I'm going to take my lemonade, and I'm going to set up a stall in the middle of Woolworths, and I'm going to sell lemonade. My little selling lemonade is going to interfere with their big selling everything else, and I will very promptly experience a force out of the door. They will not allow me, without permission, to set up a stand in the middle of Woolworths and sell lemonade. It's not going to happen. You could imagine this for almost anything else. I used the example just the other day with regards to Spur. You can't set up a Boerewors stand in the middle of a Spur restaurant. You're going to experience a force out the door very promptly. What you're doing will interfere with what they're doing. Okay, same idea here. The magnetic field around the current carrying conductor experiences a force because it interferes with the magnetic field that's generated between a north and a south pole. Now, quite often, this north and south pole, the way that we get that magnet created is possibly using an electromagnet. It's usually a bigger field, but the point is it's there, and the two of them interfere. Now, I would like everybody right now, and I'm really sorry for anyone who's really fussed about drawing on their hands, but I'm going to ask you to, just for tonight, to quickly draw on your hands. What I'm going to ask you to do is, you're going to be using Fleming's left hand motor rule. So you are going to take your fingers, and on your thumb, you are going to write the letter F. On your index finger, your pointer finger, you're going to write the letter B. And on your middle finger, this one, you're going to write the letter I. F-B-I. You are then going to take your fingers, like you can hopefully see I'm doing, and you're going to hold them all at 90 degrees to each other. This is what we call orthogonal, 90 degrees to 90 degrees. I think you haven't seen that one, to 90 degrees. In fact, you normally have to do it just a little bit till it hurts. And it's got to be your left hand. You're pulling them just a little bit tightly. You should find that it hurts a tiny bit, but you got a nice 90 degree. These letters stand for the following. Now, I know a number of schools do these differently and use different letters. Whatever you use, as long as you're sure of it, will work. I prefer this because you're using the actual letters that things stand for. F stands for force. B is the magnetic field. It's technically magnetic field strength, but we're just going to go with the direction of magnetic field. And I is the direction of the current. Just a little reminder again, your magnetic field always points towards south. And your current is always from the positive terminal of the battery around the circuit to the negative terminal. So if you all look at this diagram that I've created here, You take your lovely FBI fingers. Now it's a little bit tricky. I hate teaching this section where I'm not in front of you because I always panic that my photo gets mirrored and you guys aren't seeing exactly what I'm seeing. But I think you are. Okay, so there may be a mirror effect here, but as long as you're following what I'm doing, or at least looking at the screen yourself and doing the same. My question here is, which way is the force? So this is, the thumb is going to be the last thing that I move. The first thing that I'm going to do is I'm going to take my B finger, which is my index finger, and I'm going to, according to this diagram over here, please all keep your eyes on that diagram there, I'm going to make my index finger point towards south. My index finger on my picture points towards south. My current, in this case, is going away from me, which means it needs to go into the page. So keeping this finger pointing towards south, I'm going to turn my hand around and make sure that my current goes into the page. And then if you look there, my thumb, which is my force, points downwards, which means that everything that I've just told you, without drawing a diagram, sorry, that was a little bit of scribbling, without drawing a diagram, you could work out that the direction downwards would be the direction that your force works in or moves in. All right. Can I ask everybody at this point to quickly take a screenshot if you need to, because I'm going to stop sharing in just a second. Okay. Can I ask just quickly, who has already done this before? Okay. Is there anyone where this is, or the way that I've explained it is a little bit different? If it is, and I really do need to caution you on this, different teachers do slightly different methods. If you find that what your teacher teaches you gets the same result but is different and you find it easier, please do not change at this point in the year. If what your teacher has done up till now, or you haven't had a teacher teach you how to do it, then please just take this as one of the options that you can use. It's the one that I personally find to be the easiest, but it very much is an opinion thing. I unfortunately can't teach you any other methods because once I found something that works for me, I don't really bother to learn about the other methods. And I must be honest, I haven't yet found too many students who find that this isn't the easiest way. I think it's generally one of the accepted ways, but they're different letters. I've seen versions where it's thumb is for thrust, and I don't even know what the other letters are, but they're the same principles, just different letters. So I find FBI is nice and easy to remember. But once again, in order to use it, you've got to remember it. So if you're not going to remember it, then please find something else that you will remember. Okay, now before we jump too much further into this, I just want to check that everybody here can actually apply what I've just taught you. So if we've got a north there and a south there, and I tell you that the current carrying conductor is going the page, you should hopefully know that in this case, because we see the dot, is coming out of the page. So we've got a current carrying conductor with the current coming out of the page. My question to you is, which way, A or B, are we going to experience a force? Okay, I've just had a question that I think I need to reply to immediately, which says, is there a difference between the left-hand rule and the right-hand rule, or is it the same thing? Please note, motors use left-hand rule. Generators, which I'm going to get to later, use right-hand rule. And I'm going to explain to you why they're different rules for different things. They're pretty much the exact opposite of each other, which means that if you use the wrong hand, you're going to get it wrong. So what we've been dealing with so far has your right hand is in a thumbs up still to determine the direction of the magnetic field, and your left hand is the only hand you've got free. These two hands, drawn as well, not drawn, as I'm showing you in the video, these two hands, like this, are the ones that we use for motors. Generators, we're going to flip around and we're only going to use our, let's get this right, we're only going to use our right hand. Then it's our right hand dynamo rule. All right, so can I ask, does anyone have an opinion as to which way round the force is going to be? Okay, I've got somebody who says B. Okay, so my advice to get this right, let's see. B, B, B. Okay, you guys are quite clear that it's B. Let's try FBI. I'm going to now go and say my magnetic field, B, points down. Sometimes you look very funny when you do this. My current is coming towards me, and yes, you're 100% right. My force will be towards the right. Just something to sometimes save you a little bit of time. on these kind of questions in an exam is that your different components, so that's your current, your magnetic field, current magnetic field, and force, must all be at 90 degrees to each other. So if one of them is going up and down, I'm in fact going to put it on the diagram. Over here, my magnetic field is going up and down. My current is going in and out. Therefore, it can only be left or right. Because multiple choices usually need 4 options, you can often take your answer down to 50-50 just by going and saying, listen, up and down is already taken care of, in and out is taken care of. The only way the force can be is left or right. Let's quickly do one more here. So if I've got a north here and a south here, and I tell you that the current goes this way, my options for you here is the force going to be out of the page, or will the force be into the page? Quickly have a look and tell me what you think it is. I think I've already got it. Good. Okay. So the question here, sorry, that is correct, everybody. By the way, the answers that you've got, which are into the page, is correct. So my answer here is into the page, which will look like that. So there's a question from Rebecca saying, ma'am, in the exam, will they show the X and the dot between the north and south? Sometimes. So this type of question, exactly as I've shown you here, can be asked, but it's usually asked in the multiple choice section of the whole bit of everything together. So it's likely to be in the multiple choice, and they literally will have 4 possible options. It's not asked every single time, so I'd say I see these maybe 1 in every 10 papers. Not highly likely, but it can be asked. What we're now going to do is we're actually going to apply this in a motor. So I just need you so far to get the idea that there's a link between the current through the conductor, which creates a magnetic field, the external magnetic field, and the direction of the force that it experiences. All right, I hope that everybody is still with me at this point, because I'm about to jump into how a motor actually works. Because up till now, what we've done is we've looked at the magnetic field around a current carrying conductor. We've looked at the motor effect, which says that that current carrying conductor will experience a force in an external magnetic field. Now we're going to say, how can we be smart and use this force to actually make something that works for us? Now, you're rather lucky. I don't actually have a whole bunch of toys at school, but at home I always do, because my children love science-based toys, and they've got tons of them. So this over here is a motor. And many of you may have seen them. They're rather small, they're rather useful, and this is part of a click-together electronics kit that my son owns, and I actually had to, it's a press stud together electronics kit. So instead of having connecting wires, you just press stud your whole kit together. And that is actually, I don't know if you can see it there, but that is rotating. So to give you an idea that it is rotating, I'm just quickly going to open it up. I'm probably going to have to put the whole circuit together again now. There's a lovely little fan that you stick on the top. Sorry, I don't have switches here. Everything just gets press studded together. But when I do, can you see that connection there? Oh, woo! It moves. I don't know if everybody managed to see that. I'm going to just quickly have to stop sharing for a second. Can I check? Did everybody see it fly off, or was I too low and you didn't get to see it? Did anyone see it fly off? Okay, you did see it fly off. So basically what happens is when I close this, you can probably even hear it. Okay, so you can see that the thing rotates, and that little fan at the top is actually supposed to be there. So if you get it going enough, the thing gets excited and it flies off into the air. Okay, exciting things for little children. So this is our motor. Now we're going to be looking at how we make a motor and how it functions. The motor in here isn't exactly the same as the motor that we're talking about, but the principles are the same. All right, so the first thing that you need in a motor, and please don't get grumpy with me, I'm building my motor bit by bit. I like to explain what we're doing as we build it. We're going to have a north and a south pole. These can always be swapped around, and usually they'll be drawn exactly like this. So we very seldom have north and south this way. We tend to like them that way. Then what we're going to have is we're going to have a piece of wire that goes around in a coil. Please note, this is all flat. So if we were to view this setup from down here, oh, there's my eye. If we were to view it from here, it would all be flat on one level. So we'd just see this wire going around like this, that's a flat wire. So this is just a single piece of wire bent around into a shape like that, and it's flat, planar. Okay, so that piece of wire goes in there. Now, I want you to just please trust me for a second. I'm going to draw the rest of it just now, but I want you to understand here that we're going to just, I'm telling you that this is positive and this is negative. That means if this is positive and this is negative, the current is going to come up through this side, go around there, and come down through that side. So that's the direction in which the current flows around the circuit. I'd like us together right now to determine whether this branch here, which I'm going to call AB, and this side of the other bit of the, we call this the armature, by the way, the coil or the armature. Okay, it's a piece of wire in a coil, usually made out of copper. We're going to call this CD. I want us to work out which way the force will be on AB and which way the force will be on CD. So let's start with AB. FBI. My magnetic field points towards south, so it must point towards your right. My current, which is my middle finger, must go up towards the top of the page, which means that my thumb, which is my force, should go into the page. So this over here will experience a force into the page. I'm going to write out force into the page because if I draw an arrow like that, it actually gets very confusing that it's into the page. Then I want to go around to the other side, which is CD. So if we look at CD, we're going to do the same exercise. Our magnetic field points towards south. Our current goes down from C to D. And my force is towards myself. My thumb is sticking towards my face. So this over here tells me that the force on this side is out of the page. Okay, which means that if my arms here represented A, B, C, D, this would be moving, and I'm hoping it looks like this to you. Probably won't, it'll go the other way around, but this is going around like that. Okay, so we've got a rotation. This is coming, this side is going away from me, and this side is going towards me, so it's turning. So we can already see by having a coil of wire which wraps around in a loop that one side will experience a force into the page and one side will experience a force out of the page. Okay, now we have a couple of problems with this. I've actually seen recently a set of notes that explained a far better explanation as to why we have the commutator, but I've always gone and said if you have a piece of wire, I'm just going to stop sharing for a second and I'm going to ask you to join me or to watch me, is if you have your two arms stretched out like this, and we're not going to rotate your arms, and we're going to rotate your arms, and we're going to rotate your arms, you find very quickly that you've got a problem because the wires can only rotate so many times before they're literally going to snap. I always use the example years and years ago, we had an electronic microscope, and it had a little light. And the light could rotate because you could actually rotate it. But if we rotated the light so much that we started wearing down the insulation, we actually broke the electrical wiring by just rotating this poor little thing around and wrapping the wires so tight around each other that they snapped. So I always say here that one of the reasons that we actually need something here is to make sure that we can keep rotating this. The second reason that probably makes more sense is we want to make sure that the current always goes up on this side and down on this side. We want our motor to rotate in one direction and one direction only. This kind of motor, by the way, is called a DC motor. DC stands for direct current, and it is a direct current motor because we are going to actually supply a direct current to it in the form of a battery. Batteries are always direct current. They can't change which is their positive and negative terminal. If you think about what you know from your galvanic cells, one electrode is positive, one electrode is negative, and it doesn't flip-flop and swap around. So the way that we make sure that this component can turn around, as well as that the current that comes up the left-hand side will always be in one direction and down the right-hand side, close to the south will always be in the other direction, is by using a split ring commutator. Okay, some people call it, yeah, a commutator on its own, but I prefer to call this a split ring commutator. Okay, now a couple of ideas here. Split ring is because it's literally like my hands here. It's a ring that is got a gap between the top and a gap between the bottom. I'll explain to you just now why we need that gap between the bottom and the top. And a commutator in electricity is often anything that turns one kind of energy into another. It's just one of the words that you can know here. You can get away with saying just a commutator, but I'm going to advise to make sure that you don't mess up that it's better to say split ring commutator always. Now this split ring commutator is joined on to this entire branch here, but at 90 degrees. So you could almost imagine that if these are my split rings here with my hands, my arms here and here, which are at 90 degrees to the ring, are going to go up there. So this bit here and this entire flat coil is at 90 degrees, and these two stick up from it this way. Okay. Then what we have is we need to make sure that we can rotate this entire system, which is one piece, inside, well, I guess a circuit. So in order to keep electrical contact, we use carbon brushes. And these carbon brushes are made out of very foamy, I'm going to go with the word foamy. They're made out of very foamy graphite. So because of that, don't imagine too much into the foamy, they're made out of graphite so that this entire metal round part can move, maintaining contact with the carbon brushes, but without creating too much friction. As it is, graphite is incredibly smooth, and if you've got slightly foamy graphite, please don't ever write the word foamy in your exams, probably should take that out. But it just helps to create the idea of why we're describing them as being brushes, not like solid chunks of carbon, okay? So those allow this inside loop, along with its entire armature, to turn around while still maintaining electrical contact. This is then connected to a power supply. That power supply has to have a positive end and a negative end there, okay? The positive end is how I knew that the current went up through there, round there, in, up here, round, 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 down here and out. Now, as this coil here rotates, what you're going to find is sometimes it's not perfectly there, it's slightly off at an angle. But whether this carbon brush makes contact at this point or this point or this point or this point or this point, anywhere around there, it's still going to cause the current to go around in one specific direction. So the current, this positive terminal, will always be connected to whichever part of the split ring is on this side. When we hit this brief gap, which I've drawn rather pronounced, but the gap there and there, when we hit that gap, what's going to happen is very temporarily there will be no current, which means there will be no force. However, momentum helps to keep the coil turning around. All right. So at this point, what I hope you can understand from what we've looked at so far today is that the magnetic field around a current carrying conductor interferes with the external magnetic field to create a force. When we combine two forces, because of current traveling in opposite directions through a coil in the presence of an external magnetic field, we can create something which turns around, 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 and actually can power a little fan, electric toy wheels on a car, a washing machine, an electric car, all sorts of things, anything that needs rotation in only one direction. Please note, I've thought about it long and hard. Maybe some of you will think of something that I haven't, but we usually don't bother with AC motors. Okay, we usually actually do an inverter to turn them into DC, or we alternatively, I guess, do maybe work them the other way around. But most things want to rotate in one direction. The only example of something I've ever thought of that rotates in two directions is my washing machine. It does this funny thing where it weighs the clothes and it goes forwards, backwards, forwards, backwards. That is the only example that I've decently come up with which changes every 180 degrees in terms of direction. It isn't very logical. Things like to go in one direction or the other direction, but not one half, half, half. All right. Ladies and gentlemen, we're nearly done with this. The last thing that we need to do, so I've so far named the little parts here. Okay, we've got a cell here. Please note if it's more than one, we'd have a battery. We got our connecting wires, we got our carbon brushes, we got our split ring commutator. I'm just going to tell you a little secret that I always use to remind me which way things go. Split ring is one ring, which means that it has one direction. Okay, which is how you know that it's going to be, in this case, DC or rotate in specifically one direction. Oh, there we go. Okay, Emma's just said windscreen wipers. Windscreen wipers could be, possibly. Thank you. I'm going to have to actually go and research that. That's a good idea. Windscreen wipers may be something that flips backwards and forwards. Could be. All right. So the last typical question that they like to ask you is how can you increase, oh no, I'm lost for a word. I don't know if it's a power. How can you increase, we're going to go with the speed of rotation. The speed of rotation or possibly the power of a motor. Okay, so how can we make the motor more powerful? Well, there are a couple of things. The first thing that you can do is you can increase the current. Please note the easiest way to increase the current is to put in more voltage in the external cell. Motors always turn electrical energy into mechanical energy. This means that since motors turn electrical energy into mechanical energy, they will always have a power source. We're never not going to have a power source. So we can increase the current by using a stronger cell. The second thing that we can do is that we can use stronger magnets. Typically, if these are also connected to an electromagnet, we can make our electromagnets stronger. Okay? So those are the two obvious things. Then we hit the unusual things that are a little bit different. The first thing that we can do is we can use more coils, or sometimes we use the term turns. So instead of just having one piece of wire going around here, what about if we had 2 or 3 or 4 or 20 or 200? What about if we had more turns of the wire, or even just more turns of the wire going around in one direction? You can actually make a very simple motor yourself, just taking copper wire, wrapping it around and putting it in an external magnetic field. It is possible for you to do. And usually what you'd do is you'd actually wind, I don't even know what you wind it around, but you wind it around repeatedly, and you'd have many, many turns, because each of these coils will experience the same force. So if you've got 10 coils, you've got 10 times the force, okay? And then the last thing that you can do here is you can use curved magnets. So the thing about curved magnets, and I'm now going to just deviate a little bit here, is we need to understand certain things about when this force will be the greatest, which brings in a whole bunch of other things that I fortunately overlooked teaching you up until this point, because I didn't want to make things too complicated. The greatest force will be when your current is at 90 degrees to your magnetic field, which is one of the reasons why from B to C and A to D, there is no force experienced. There, the current runs parallel to the magnetic field. The two don't cross each other at 90 degrees, and we're not going to end up with any force being induced. So there isn't going to be any motor effect, okay? Now, in order, if we have curved magnets, if, for example, here's a curved magnet, and here's another curved magnet, and this could still be north and this could still be south. If my coil is at that angle there, and let's say for the sake of things, I hope you all understand that that coil is me looking at where BC lies, and you'd actually have these pieces coming towards us here to make up the rest of the coil. So it kind of looks something like, or very badly drawn like that. if you've got these, you can still have a north to south magnetic field there. So what was drawn across here can now be drawn across there, which means that we can have this current at 90 degrees to the magnetic field for longer. So the more curved we can make our magnets, the longer we can end up with the maximum force. Okay, now just a couple of important things. We had to have this gap. If we didn't, we would create a short circuit and the current would go zips straight across and down here. It would just go round and round here. It wouldn't bother going through the armature at all, because why would it go through the armature if there wasn't a gap here for the current to get through? Okay, so that's just something worth noting, otherwise we end up with a short circuit. All right. Okay, I think I'm going to stop at this point and I'm just going to quickly check with everybody that I've covered everything. Ma'am, what about brushless motors? Do we need to know anything about those? As are not in our syllabus, I've never ever seen it. I'm pretty sure that there are a million different types of more updated technology that exist and they're not part of the syllabus. You will be examined and every single circuit that you have will have to have something where your split ring connects to your external circuit and allows rotation, and we only teach about carbon brushes. I'm sure that there must be other things out there, but you're never going to be, well, touch wood, you're never going to be examined on them. Okay, I haven't seen it come up anywhere. All right. Ladies and gentlemen, can I just double check? Is there anything else that you feel or you've heard about motors that you feel I should touch on right now? Because I think I've covered all of my bases. As I mentioned right at the beginning, motors is not their focus. I've searched, oh gosh, all the way back to 2014, and I think there are 4 long questions that include motors. Usually your motor will be put in as a multiple choice question, and in fact, after having done this entire nearly 50-minute lesson on motors, you're probably going to curse me in that exam when you go, wow, we did all of that. But I promise, as I said at the beginning, it makes the idea of generators a lot more palatable, which is why I teach it this way. All right. Some of the people who do IEB would need to know things in more detail. Do you need to know graphs for motors? There aren't really graphs for motors because the graph here would be showing a force and it's not showing a current. So there will be graphs for our generators, definitely. Okay, you need to know both your alternating and direct current generator graphs, but generally we don't have graphs for motors because you'd be looking at the force or the speed of rotation, and they generally don't ask anything on that. In fact, to the point where if you ask me to draw a graph or give you an example of a question, I can't. Okay, not offhand. All right, ladies and gentlemen, I think at this point we have just finished motors, nearly. Does the speed of rotation to the refer? Now, Iman, just quickly here with regards to the speed of rotation, I can't remember the terminology of what they usually ask, which is why I was sitting here going, how do we make, they usually say, how do we make the motor more powerful? But more powerful motor is something that turns faster, okay? Or can lift a larger load, which is because it turns faster. So I'm not certain as to exactly which terminology they use. Basically, if they ask you, how do you make your motor better? That's what we're looking at. Okay, so, I just pushed the wrong button. I'm going to stop sharing for just a second, and I'm going to suggest to everybody that you please quickly stand up and stretch your legs, because we're going to get moving on with generators in just a second. All right, so quickly stand up. I'm doing the same so that I don't end up with a numb bum. And then we can keep going. Okay. I hope you all had a good stretch and you're still with me and you're still awake. Okay, let's carry on. All right, what we're now going to be moving on to is we're going to be moving on to generators. Please, within generators, there are 2 kinds of generators. So just like in electrodynamics, which is a section we've been doing, we started with motors and we did generators, and they're kind of opposites of each other. Here we're going to split into AC and DC generators. So I'm going to start with a DC generator, and I'm also going to look at an AC generator. There are two specific words that they actually use to describe these. For some reason, we don't teach them in the local syllabus, but I find they're worth covering for us. A DC generator is known as a dynamo, and an AC generator is an alternator. Okay, please, that is not something that we specifically teach you, so don't go and say it out loud, but it's just something for you to know at the back of your head, and I find it's really convenient to remember because D goes with D and A goes with A. Now, the difference between a DC and an AC generator has to do with how the current works. Both types of generators, whether they're DC or AC, convert kinetic energy, technically mechanical energy, into electrical energy. The difference is what kind of current we get from them. So a DC generator produces direct current. An AC generator produces alternating current. Then we're going to go into a little bit more detail. I'd like to assume that at this point, just before prelims, all of you already know these terms, but I think this year has been a little bit crazy. So there's a small chance that we didn't get there or you didn't get there. So if we're talking about direct current, it means that the current flows in only one direction. And an AC means that the current alternates or changes direction every 180 degrees. In South Africa, we focus quite a lot on alternating current generation because it's really easy for us to transport alternating current. What I am going to do, I think we're not going to get to the section on AC today. It'll probably only be on Thursday. But when we get there, we'll look at a whole bunch of the equations and calculations which are linked to alternating current. So it is important that you know that. I find when I teach this, the difference between AC and DC, it actually helps to immediately jump in and hit the nail on the head and tell you what the difference is between them. So DC has one direction. I told you just a few minutes ago that one direction needs one ring. So this means, and that actually has been very badly drawn because the lines from the side shouldn't be there, but there we go. This means that when we do this, I don't know why this keeps going around, we are going to use a split ring. So we're going to use split ring commutator. One ring, one direction. When we do our AC generator, we're going to do two rings and two directions, and these are called slip rings. Okay, technically when I was at school, we used to call them slip ring commutators, but I believe that the terminology that's now accepted is if you just call them slip rings. If you call them slip ring commutators, that's fine too. So the idea here is, unlike us having a component which goes up and joins a little bit like this, I usually actually draw this going inwards and upwards rather than out on the outside. That's why my thing looked a little bit funny the way that it was. There we go. So with my slip rings, the idea is that we have one ring which goes out and at 90 degrees makes a circle. So the idea here is that this circle is perpendicular to this point of attachment that goes through it. Then we have another piece of wire that passes through the first, goes out and goes around in such a way that this circle is at 90 degrees to the rest of it. And what you'll see here is the one ring slips through the other. So with slip rings, we have two rings, which means two directions. Now, ladies and gentlemen, I wish I could draw in 3 dimensions. I can't. What I can do is draw what I like to think is a really good two-dimensional representation of these. So I'm going to quickly go through how both the split rings and the slip rings produce current that goes in alternating directions. I am going to show you all of that. But first, we need to go backwards and we actually need to talk about what drives a generator. Because while it's very quick and easy to go into how it works, we're going to quickly have to look at why it works. So, generators work based on the principle of electromagnetic induction. Just like a motor works based on the motor effect, generators work based on electromagnetic induction. And electromagnetic induction basically comes with the idea that if you move a piece of wire in a magnetic field, a current will be induced. This, I guess, is effectively the opposite of the motor effect, which says if you have a current carrying conductor in a magnetic field, it creates a force. Now we're saying if you move it, which is if you put in the force and there's a magnetic field, we're going to have a current that gets created. To add on to that, or to explain it further, we have Faraday's law. And Faraday's law explains basically that the reason why the current is induced is it isn't actually a current that's induced, it is an electromotive force, an EMF is induced. So we get energy being supplied in our form of EMF, and that EMF, if you've got a closed circuit, will cause current to flow. So Faraday's law, which by the way you do need to know, okay? So if they ask you specifically for the law, you say Faraday's law. If they ask you for the principle, you say electromagnetic induction. Two key words. Sometimes they accept both in an answer for a question, but if they say a law, they specifically want Faraday's or Lenz's law, and it's usually Faraday's law. So Faraday's law says that the induced EMF is directly proportional to the rate of change of magnetic flux linkage. In grade 11, you probably covered a nasty equation, which I think some of you still freak out about, which basically said that EMF was equal to the change in magnetic flux over the change in time. And you also looked at the fact that the change in magnetic flux was equal to AB. And then I always hate this because I forget if it was sine or cos, but I think it was cos theta. And there's this whole complicated thing. Fantastic news, matric. Don't need to know it, gone, okay? All that you need to know is that if you can change the magnetic field faster, you will get a greater EMF. That is the point to which you need to understand this idea, okay? There is also Lenz's law that pops into here just lightly, but usually I find that I can teach you generators perfectly well without Lenz's law. So all that Lenz's law does, if I bring it in here quickly, is that Lenz's law says that the induced current or EMF, the induced current flows in a direction so as to oppose the effect creating it. Okay, which sounds very much, if you think about it, like Le Chatelier's principle. There's a disturbance, it's going to counteract the disturbance, and that's kind of where Lenz's law comes in. So Lenz's law explains that unlike your Fleming's left-hand motor rule, your right-hand dynamo rule is going to be here. force is in the same direction, magnetic field is in the same direction, but your currents swap direction. Please, can I ask you at this point to quickly take a screenshot if you need anything from the page, because I'm going to go and quickly draw a diagram to explain Lenz's law to you. Okay. So, no offense to all the women out there, but I think Lenz's law often behaves, or the situation around Lenz's law often behaves like women do. Okay. Gentlemen will probably agree with me. Ladies, if you disagree with me, you're welcome to discuss it later. But I think it kind of makes sense. Quite often women don't even know what we want. So if we have a solenoid, now a solenoid is effectively, here's me going to get myself into trouble again. A solenoid is something that's just like a central coil. So, sorry, not a central coil, like a central support. So you can imagine a toilet roll or a piece of plastic with a whole bunch of wire wrapped around it continuously in one direction. Okay, so I'm drawing a very simplistic solenoid here. Okay, there is my solenoid. Okay, so please note that piece of wire goes around the back and front, and then here to the front, right at the beginning. Now, if I bring in a magnet, now I have a magnet with a north end and a south end, and I bring the magnet towards here. What is going to happen is we're going to have a changing magnetic field. I'm going to quickly explain to you why we have a changing magnetic field. So you hopefully all know that a magnetic field goes in towards the south. So if I draw, I'm just going to move this away. I'm going to actually physically move it in just a second. If I draw my magnetic field, the magnetic field lines go towards south, then we're going to start having them curl in towards south. Okay, this is a little bit for the IEB students as well. We're going to quickly be looking at what magnetic flux linkage means. Now, magnetic flux linkage is a very complicated concept. I describe magnetic flux linkage rather simply as the number of field lines that cut through a surface area. So here's my area. It's this round coil here. And I want you to see as I move this magnet, which I'm hoping to be able to move in one piece, as I move this closer in and further out and closer in and further out and closer in and further out, you'll see that initially there are probably only 2 lines that cut through that area. But as I bring it in, we're now going to have 4 lines, 5 lines, 6 lines, and then I take it out. So as I'm moving this magnet in and out here, the magnetic flux linkage is changing because more of my field lines, my magnetic field lines, are cutting through the area. Now we can also change the magnetic flux by making this magnet stronger, weaker, or possibly if we were to go and alternate this coil and make it go strangely down at an angle. All right, so if we were to look at this, that's how we change our magnetic flux. So I want you to just have that little bit of a mental picture of why it is that something's happening here. Okay, so we're changing our magnetic flux, which according to Faraday is what you need to do to induce an EMF. So this is where Lenz comes in. Lenz's law says we're bringing the magnet closer. Okay, so the effect that we're creating is we're bringing in a south pole. Now this is where this magnet's a little bit naughty and like a woman sometimes. Some men probably do the same, but I generally find women tend to have the reputation. I bring in a south pole, the magnet goes, we don't want any south poles here, go away. Okay, and it will do this by creating a south pole here and a north pole here. You don't actually need to know this, but in order to do that, we can actually use a solenoid rule, which is shown with our right hand. Our thumb points towards north, and in this particular case, it tells me that the current for this entire thing is going to flow around in this direction. Cool. So we bring in a south pole, and what it does is it actually gets the current to flow through the solenoid in such a direction as to generate a south pole here to repel the south. Okay, a little bit catty there. So what ends up happening is that we actually have to do work to bring this magnet in. W is equal to F delta X cos theta. Since we are experiencing a force that is in the opposite direction to the displacement, we need to do work to bring this in. This is how we are turning our mechanical energy, because we are doing work, into electrical energy. We are not doing magic. We are not doing anything funny here. We are literally turning one form of energy into another. And the reason that this form of energy arises is because when the current flows here to be able to create the south to repel this one coming in, it means that we're going to have to do work against the magnetic field to bring this magnet in. Okay, that is why years ago they actually thought, rather interestingly enough, that this was magic. We were doing magic. We were making energy out of nothing. And we now know we're actually just putting in the energy by working against the force. Okay, just wait a second. Somebody said, doesn't the current go in the opposite direction? No, I'm using my right hand here. So it's the right hand solenoid rule. My thumb is pointing towards north. It goes around and over the front. This is the only bit where it goes over the front. I'm pretty sure that I've got this the right way around. Good news, only IB students care whether I've got it the right way around or not. NSC students, it's not part of what you need to know. Okay, so what we're now going to do is we're going to take the magnet out. Okay, so we've given up. We've decided that this magnet, we're wasting our time, so we start removing the magnet, which effectively means that we are now pulling it that way. Okay, and this is where we get really technical. Not really, really mean to saying horrible things about girls changing their minds. But we bring out the south and suddenly the situation's, no, don't take the south away. I've changed my mind, come back again. Okay, so what's going to happen here is that all of the current is going to turn around. So we can now create a north pole on this end, and to create a north pole on this end, the current is going to turn around through all of these branches there. Okay, and the current will flow in the opposite direction. But once again, we are now having to do a situation where the displacement and the force are in opposite directions. So we are losing our kinetic energy, and our kinetic energy is going to be converted into electrical energy. If you think about it, if these two are in opposite directions, your cos becomes 180 degrees, and that is where we do the work with the energy. It's also why you're going to find that the direction of the current is always in the opposite direction to what's creating it, and why when we do these two fingers, the currents flow in opposite directions for Lenz's law. Okay, please, if you need to take a screenshot, quickly do. I want to just quickly ask a couple of questions before we go any further. Who has already learned something new today that they didn't know or didn't remember? Okay, so Iman, just quickly, the theta is always 180 degrees. That's what Lenz's law is trying to do, or ends up doing. It isn't really what we technically learn from it, but it's what we end up doing. Okay, brilliant. I'm glad that so many of you learned so much. Okay, so now I said I'd go back and I'd show you how the split rings and the slip rings work, so that you have a picture in your head that actually makes sense. So I'm going to draw a north pole and a south pole. Please remember, this is my flattened pancake version of this armature setup. So over here I have a north and a south pole. I'm going to call this A, B, C, D. I'm going to draw this going around. There's my split ring. Going around, there's my split ring. There's my carbon brushes and my carbon brushes. And there's my power source, positive and negative. This should look exactly like we had before. So if we look at the specific situation, positive to negative, the current goes in here, touches there, round, up there, goes down there. If we use our, sorry, this is generator. I'm going the wrong way around for generators. Sorry, ladies and gentlemen, it's been a long evening. Let me go back and let me not put in a cell, because we're doing generators and I'm about to do motors for the second time. If we go and put in a voltmeter here, we could technically put in an ammeter, current could technically flow, anything like that. Okay, so I'm going to draw this and we're going to imagine that this is moving around an axle in one specific direction. So what turns this axle could be anything. It could be turning water in a hydroelectric plant. It could be boiling steam in any kind of, I guess, power producing company, whether we're using nuclear energy to boil the steam, or whether we're using coal to boil the steam, or whether we're burning biofuel to boil the steam, we're still boiling steam and the steam's still turning a turbine. We could use children in a playground where they're on a merry-go-round and they go round and round and round and they create electricity. We could use this as they do in a couple of the gyms where people cycling on bicycles create rotational energy, which power the bicycles and in some places actually power the lights, okay? So any of those could be used. I'm now going to show you what happens 180 degrees and then we're going to fill in everything. Here we got north, here we've got south, here we've got DCBA. Remember, it's gone around 180 degrees and we're still rotating it in one direction. We've got this bit here, we got that bit there, excuse the bad drawing. We got our 2 carbon brushes and we connect up to the voltmeter. Just as a hint, one of the ways that you often know that this is a generator, not a motor, is that it's got a voltmeter and it doesn't have a power supply. So this could have a voltmeter, it could also have an ammeter, it could actually have a light bulb which it powers, or in the case of a giant power station like Eskom, it could be whatever it's linked to. Okay, so right now the fact that you can watch me on your computers at home tells me that you watching on TV, well not you, your computer that you're watching on could be that component there that we're looking at. So what we're going to do now with the generator is we're going to be focusing on the left-hand motor rule. So we're going to do the right-hand dynamo rule. With our right-hand dynamo rule, it looks exactly the same. F for force, B for magnetic field, I for current. Same idea. You got to make sure you swap hands because if you don't, you're going to get it all completely wrong. Now, I would like you very much to go across to this diagram here and try and work out which way round all of the force is going. Sorry, the current is going. So if this is being pushed, so I'm going to say here that this bit here is coming out of the page. Actually, let's look at that carefully. It's always very tricky when you've got a circle around there. So I'm instead going to tell you which way these are going. It's my intention that this side is coming out of the page, so towards you, and this side is going into the page. Gets very tricky to draw it. So this coming out of the page means it's coming out. This is going in, but it often is hard to tell if you're in front or behind. So if we're dealing with A to B coming out of the page, the force is towards us. Make sure you're on your right hand. The magnetic field goes towards south, which means that my current goes from A to B. So my current goes this way. Going on the other side, it's going into the page. So the force is away from me into the page. Towards south, oh gosh, you can't see my hand there. Towards south is my magnetic field, and my current pointing down is over there. So that tells me that my current goes this way. Please note when we get back to here, 180 degrees later, this is still out of the page. This is still into the page. So what we end up with here is that the current will go in the exact same direction. Now you've got to follow backwards to make sure you understand which side is positive and which is negative. If we go backwards here, backwards here, backwards here, backwards here, backwards here, this side must be the positive. In fact, we can even say the positive end there. If we go forwards all the way to the end, we can see that that is the negative terminal. And you'll see here, but even though this is switched around 180 degrees, that this is now going to be positive and this is now going to be negative. All right. Please note if this is being rotated in the same direction continuously, the current through the branches of the armature is always going to remain the same. So far, all that this shows you is that if you've got a generator, specifically in this case, a generator with 2 split rings, which will be your DC generator, then we're going to end up producing direct current. What the direct current graph looks like, especially if I try and draw it a little bit straighter. Well, that wasn't what I was aiming to do. Let's try there. Okay, a little bit straighter. It's a new line, not the same line. Okay, so if we plot a graph here of either potential difference or current against time, what we're going to find is that the graph goes like this, bunny hops. Okay, the reason that it decreases, goes to a maximum and then decreases to a minimum is, remember, you're only going to get your maximum when they're at 90 degrees to each other. As we go up, we have less of a component that's at perpendicular, so it's going to become less, 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 and this value of 0 happens here, here, and here when the splits come into contact with the carbon brushes. If you think about it, at that brief instant in time, there is not going to be any current that is going to be able to flow through the external circuit. The split is going to be what's in contact with the external circuit, so no current flows. Now, just something that is essential that you get here. 2 of these makes 1 period. Please, 2 of them. Not, this isn't 1 period and 1 period. This is 0 to 180 degrees, and this is the way to 360. So this is the first half of the rotation, and this would then be to return back to there. So you'd go there to there, then there, back to there, and the full rotation takes 2 bunny hops. Okay, all right. This is what we'd usually call the V max, or the maximum voltage, but we're not really going to be looking too much at this in terms of DC generation. It's more going to be in terms of alternating current generation that we look at everything like this. All right, does everybody understand at this point how a DC generator works? And can you see that using the split rings is going to allow us to always have 1 terminal positive and 1 terminal negative, but we don't end up producing a fixed constant voltage or fixed amount of current. It will dip down. Sometimes they use things like capacitors to kind of boost it in between so that you don't have as much of a dip, and then you kind of end up with these little waves instead. So it isn't like bunny hops, it's more like small dips. But you don't really learn about how we use capacitors, so you don't need to worry. That's just for general enrichment for you to know. All right, so going back to this, I'm going to adapt my screen now to show you what happens if we're going to change this from a DC generator to an AC generator. So the first thing that's going to change, not that. I did not want to get rid of that bit. It's everything else here that I wanted to get rid of. Okay, let's see if I can do this delicately so that I don't remove everything that I didn't want to get rid of. There we go, brilliant. Okay, so I wanted to show you that this bit I don't want to change. Hopefully you all are fully in line with the fact that if we're turning it in the same direction, our magnetic field is in the same direction, the current's going to be induced using FBI right hand in the same direction. What is going to be different is how our slip rings look. So the first slip ring, I go out to the side, round, make a big loop. These are exaggerated. The second one passes through the middle of the first without touching. It goes out to the side and it makes a big loop. This connects to one carbon brush. This connects to another. Now 180 degrees later, this is not going to go out towards the left anymore. It's going to go out towards the right, and it's going to make a big loop. My carbon brush hasn't moved. This has flipped from this side to this side, and instead of it going out towards the right, it's going to go out towards the left and form a big loop. This is still going to be connected to a voltmeter or a ammeter or a light bulb or whatever it powers. Okay, there's our components. Now I want to show you the magic in case you haven't seen this. If we go backwards from here to here, down, 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 that is the positive terminal. Going forwards, this is the negative terminal. Now watch the difference. If we go here and we go backwards, 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 down, this is the positive terminal. Can you see? Conventional current goes here, up, round, down, out, through to here, and this becomes our negative terminal. And what we find happens here is that when we produce our graphs, we're going to have these two swap polarity every 180 degrees, which means that the graph that we get is going to effectively be a sinusoidal graph. It's going to be like a sine graph, okay? So if I were to draw my graph here, it's gonna look like that. Okay, where if this is 0 degrees, this is 180 degrees, changing sign, this would be 360 degrees, or you could say that every 180 degrees it changes sign. Okay, this could be my potential difference or my current versus time. One full oscillation takes me, or one full rotation takes me the whole way through from there to there. Please note, when this coil is vertical, so imagine we've got our magnetic field going across this way. When the coil lines up this way at 90 degrees to it, that's when we're going to hit our 0 values. So sometimes I find there's an interesting way to view this. Do you imagine you're looking down through the thing here, and you view this as being a dot going away from you, and this as being a cross, a cross going away from you and a dot coming towards you. So when you've got it in that orientation, it might be the maximum. Okay, give me a second. Is the graph meant to be current? It doesn't actually matter. As I said, I could plot potential difference or EMF against time, or I could plot current against time. Okay, it doesn't actually matter. You'll get the same graph for both potential difference and current. Because if you've got potential difference, it'll cause the current to move, and you'll end up with the same pattern for either. So this corresponds to there, and this would then correspond to the opposite arrangement. So it's turned around 180 degrees. Since we said that we were going to be rotating this around in a clockwise direction, I've got to make sure that my graph my picture rotates in a clockwise direction. So clockwise direction means that goes there, that goes there. Over here, this represents that at the top and that at the bottom. Over here, this would look like, and I'm just going to make sure I get it the right way, dot and cross. So you can see basically we're imagining this coil turning around, turning around, turning around. So whenever we have the coil vertical, that's where we're going to hit a 0 voltage and a 0 potential difference, because you're not going to have them at 90 degrees to each other. So you're not going to have any component cutting through. And the maximum will always be where you have your coil horizontal. So effectively it cuts at 90 degrees through your magnetic field. All right. And this is the type of graph that we get. So let's go and look at the same thing that we did before. How do we make the generator more powerful, or how do we increase the current produced? So how do we increase the EMF or the current? It'll do the same thing. If you increase the EMF, you'll increase the current. So the first thing that we can do is that we can turn the coils faster. If you turn them faster, you're going to have a greater change of magnetic flux linkage, which leads to a greater EMF. The second thing that we could do is we could use stronger magnets. Please be very careful. Bigger is not stronger. You must specifically say stronger. The third thing that we could do is we could use more coils or more turns in the coil. So instead of just having one coil, we could have 20, 30, 40, 50. The more coils there are, each of them is generating an EMF, the more you'd have. And the last thing that you can mention is to use curved magnets. Same effect as before. Now, the very last thing that I want to discuss with you today, because I think we've actually done a lot of theory, and it's quite a lot more than I thought we would, which is rather encouraging, is they like asking this graph and saying what would happen if we turned the coil twice as fast. So most people are pretty quick, and they realize if you turned it twice as fast in the same amount of time, and please note my time here wouldn't be called 180, 360, it would literally be the period that we use. So if originally it had taken 2 seconds for us to do a full rotation, and please, that's a bit of an exaggeration, it's a thumbsuck number, we now have to have the entire coil rotate in 1 second. So most people are very quick to go, okay, cool, we have to go up, down, up before we get to 1 second. What they forget is if we are turning the coils faster, our EMF will also be greater. So when we do this, we're going to end up with a point there, twice as high, twice as low. And your graph should actually look like this. Where most people go wrong is they remember one of the two things. They remember to make the voltage bigger or to make the period smaller, but they don't remember to do both. So please, that's the one thing I'm going to ask you to please make sure that you remember to do. All right, can I suggest at this point that you please take a photo or a screenshot of the notes that you've got what you need. All right, I'm going to quickly get back to this. All right, so ladies and gentlemen, I hope that this all made really good sense to you and that you do have a better idea of how a motor works as well as how a generator works and how they are similar and also completely opposite of each other.